Welcome back, guys. Now we go for our first kernel-based algorithm. So my idea here is to give you the practical ideas on how to build up your first supervised learning algorithm from scratch, considering exactly the same, let's say, the same initial concepts as we consider when building up the support vector machines. So basically, you guys can see this as an introduction to support vector machines. To start, we just consider like a given bidimensional input space. Suppose I have here like temperatures, here I have like pressure or any kind of variable. And of course, given those two attributes, we've got 6 points in our space. And 3 of those points are negative, are related to the negative class, and 3 others to the positive class. So at first, we have to come up with 2 vectors, a positive central vector C plus and a negative vector C minus. This one, C plus, is going to be a position vector exactly in the average of those positive points over here, and C minus will be a position vector exactly in the average of the negative points we have in our space. You guys can see I'm just computing the sum and the average in terms of the number of positive instances I have in my problem, and here in terms of the average in terms of the negative instances I've got in my problem. I will give like a practical idea over here. So let's do like this. I'm just going to go to the codes over here. I will create an example, a third example. And in this third example, we are going to have our code, okay? So I will code, let's do this like, let's call it first algorithm .r. In here, I'm going to come up with the space. Let's say I'll define my, maybe like this. I'll define my input space X in terms of a concatenation of columns in my space. And for example, let's produce two Gaussians, okay, two random norms or Gaussian functions, whose means will be like -10, and here could be like -10 too. Yeah, could be like -10. Of course, I have to define the standard deviations. Could be like standard deviation equals to 1 and standard deviation equals to 1. And here I will define like 100 examples and another 100 examples over here. In the next line of code, I'll just come up with, okay, let's concatenate along the rows of X a different bidimensional Gaussian function. This one will have the mean equals 10 and mean equals 10. Also with 100 observations here, 100 in here. And I will create a vector Y with the classes or class labels, if you guys prefer, in which I will have the negative class label for the first bidimensional Gaussian function with 100 elements. Of course, this is a repetition of -1 100 times, and a repetition of +1 another 100 times, just to consider the 100 examples I've got here. Those are going to be considered the positive examples. I'm going to run this inside R so you guys can see what's going to happen. Of course, I have to load my first algorithm. The dimensionality of X will be 200 by 2, so I have 200 examples, 2 dimensions, of course. If I plot X, I will see 2 bidimensional Gaussian functions, as you guys can notice over here. If I plot like using PCH20 and CEX like equals 3, you better notice what's going to happen over here. Okay? So my point here is I have one class for those points over here and another class over here. Of course, the classes are defined by Y. I can plot in the same way I did here, defining colors equals Y. As you guys might see, it's just impossible to plot negative colors. So I could sum up like 1. If I sum up 1, here is going to be 0 and here is going to be 2. However, 0 cannot be plotted, as you might notice over here. So I'm going to sum up 2. And now you can see the negative examples in black and the positives in green. Okay? So now we proceed computing C plus and C minus. How can I compute those guys? So let's write here like defining our first data set. Okay? So here we have the input space of variables. This could be like one dimension, could be like temperatures, and the other could be something else like pressure, as I mentioned before. And here we have the class labels for all input examples. Of course, the input examples are defined along the rows of this matrix X. Okay? So my point here is we can plot X as we did before, defining colors equals to Y plus 2, just to correct the colors, right? PCH equals 20 and CX equals 3, just to see the points. Yeah, it could be 2. It's like too big, probably 3. So my next step is now we compute the vectors, the pair of vectors C plus and C minus. How can I compute C plus? It's kind of easy, isn't it? I'll just come up and ask like which elements in Y are equal to -1, and R is going to bring the example IDs for me. Having those IDs, what I can do is basically, okay, so now, in this case, of course, the IDs will be from 1 to 100. As you might notice, from 1 to 100 we have the negative class, and from 101 to 200 we've got the second class. So from 1 to 100, the first class. There is something really nice, which is a function called call means, or the average of calls along columns. R runs this and already compute the average for the first and the second dimensions given all negative instances. That's so nice, so good. Okay? This is going to be our C minus. I'm going to call it this, okay? What happens with our C plus? I'm worried about the positive classes. So I will just select the positive classes and of course the corresponding IDs and compute the same but for C plus. Now I have the average vector for the positive elements. I think this is a good starting point, and now we can just come up with a plot. In this case, I will plot for you something like this. Just concatenate along the rows C minus C minus, and C plus. Okay, oh, sorry guys. And C plus, both vectors. Those are the central, let's call like central points. Yeah, it could be central points. Those central points, and let's plot those central points using a different color. Could be a color equals to whatever, I don't know, like equals to 5. Okay, and of course I will define a PCH20 and probably a CX greater, could be like equals 5, so we can better see what's happening. Now I'm just going to load my code once more over here and see those average points, as you guys can see here. Here I have the average vector considering every negative vector in my space, and the average vector considering every positive element I have in my space. Colors mean negative and positive examples. Okay, just by chance I selected those colors. Okay, from that we go back to our slides, and then I'm going to find some other vectors. My point now is I must find this vector W over here. This vector W is the same as the positive central point minus the negative central point. So it's going to be a vector. If, of course, this positive central point over here is a position vector that starts at the position 0, 0 and goes up to here. And the negative happens in the same way. It starts here and it's a positive, it's a position vector that leaves the 0, 0 and goes up to this central position. So my point is when I subtract C plus from minus C minus, I will obtain this vector W over here. Of course, this point at the middle over here, it's going to be the perfect point to have a hyperplane crossing and dividing the positive side of my space from the negative side of my space. Just remember, any kind of classification algorithm you guys consider is practically doing that, just dividing the space. Having one side, try at least to have on one side all positive elements and on the other side the negative elements. And the hyperplane is this guy named O over here, okay? This point, this central point is of course C plus minus, it is the same as C plus C minus divided by 2. It's going to be the same as well. But the vector W is of course C plus minus C minus, because the direction is of course going from, it comes from the negative element to the central positive element, representing the all positive instances. As you guys might see, this is a very basic and first classifier. In this classifier, I'm just considering that I've got a central point and all positive elements are around, and a negative point and all elements are around. If I have like a very complex scenario, let's suppose that the negatives are around like this, the positive class, it's not going to work. Okay, so it's just a starting point, just like a very basic toy to start with. But it's good to start with basic examples, just to make sure we are at the same page, okay? Just go for a next step. Now consider, of course, I have this point over here, okay? If I have this point over here, and suppose this point has a position vector that leaves the 0, 0 and goes up to this central point. It's a position vector, okay? What I'm going to do now is this. Consider we have a new instance x, a new position vector leaving from 0, 0 and going to this place. This is our position vector x, starting here and going up to here. How can I classify this position vector as either negative or positive? I can just subtract it from my central point or central position vector c that starts here and goes up to here. If I subtract it from c, as c it is in here, and as x it is like this, x minus c is going to be this vector, as you guys might notice, this vector exactly. When I compute the inner product in between w and x minus c, is this going to be a positive or a negative result? Of course, I suppose you guys remember something quite basic. Suppose this, let's say like this, we've got a vector like this, and this angle is greater than 90 degrees in this scenario. As it is greater than 90 degrees, when I multiply this using our inner product by x minus c, what I'm going to have is a negative result. However, if x were in here, at this location over here, x minus c would be a vector like this, and the angle would be acute, be smaller than 90 degrees. Of course, if I multiply a vector by, if I compute the inner product or the dot product of a vector like this, having an acute angle in comparison to w, the result will be positive. So the simple result of the dot product can be used to decide if I am on this side of this hyperplane O, or if I am on the negative side. That's quite interesting. Actually, I think I can carry on here and then implement later. So the classification will be just given by this sine function. Just remember, the sine function shows me here in R, like if I try like sine of plus 500 will be 1. Sine of minus 10 will be minus 1. Sine of minus whatever will be minus 1. And sine of a positive value will be positive 1. So it's just the side of the hyperplane. Just informs us if we are on the positive or on the negative side of our space. So this hyperplane is just dividing our space in two half spaces. That's a concept. That's the technical term we use, two half spaces. How can I compute that? It's just x minus c, as you guys can see here, this vector, dot product or inner product by w, which is in here. How can I compute that? How can I solve this problem? It's not difficult to solve this problem, as you guys might notice over here. I have x minus c inner product by w. So x minus c comma w will be exactly by the distribution, will be the same x as x minus c. And how can I compute w? W is this average vector, position vector that leaves the 0, 0 and goes up to this point, central point for the positive class, minus the negative vector, negative position vector that goes up to this position. So C plus minus C minus will provide W for me. So it's kind of easy to compute this guy over here, of course, W. What can I do next? I can just distribute I can just substitute C. You guys remember what C? C is basically is just the position vector that goes up to the central point of W over here. How can I compute it? That's the same as C plus C minus, okay, divided by 2. And that's going to be a position vector exactly in the middle over here. So proceeding with the substitution of this C, I will have 1/2 times C plus C minus. That's what we have in here. What can we do at this point? We can distribute this X inner product by this C plus, this X inner product by this minus C minus. You can see here, this is allowed because of the inner product is a linear transformation. So I can follow with this step. So X inner product with C plus, it is in here, minus, okay, minus, why minus? Because here I have a minus, inner product by C minus, as shown in here. Carrying on, I can just distribute this term. This will be this term over here, okay? This term over here, inner product by this, and this term over here, inner product by this second term. But here I just decide to open in 4 terms. So over here I just use like the evidence to show minus 1/2 over here, and used C plus inner product C plus. It's here. C plus inner product C minus, but there is a negative sign here. So the negative sign appears in here, and C plus C minus. Next, C minus C plus, C minus C plus, and next, finally, C minus, but there is another negative sign over here, which is in here, and C minus. What is nice about that is, take a look, we've got C plus C minus, and we've got C minus C plus, and those, of course, the order doesn't matter in this, okay? The result will be the same, and one is negative, the other is positive, so I can cancel out those 2 terms. And I will end up with X dot product, or inner product, if you guys prefer, C plus, minus X C minus, plus Y plus, because I'm just using over here, because this guy, just remember, this guy here was negative, and this guy was positive. I just inverted, just used like minus over here multiplied by minus, that's positive, and C minus minus, as it was negative here, it's going to be positive, and this one was positive, negative, C plus, as shown. You know what's nice? This is basically what I need to compute to solve this. But I have to apply the sine function on top of this, of course. The sine function has to be applied here. Let's see the next step. So you guys might notice, oh, that's quite interesting. Yeah, I can open up this in different way. Yeah, that's just a possible way to open up. Some papers or some books will show this very same result in a different way. People are going to call this as a result of the application of W on my vector, and this as a term B. So here I'm just showing that in that kind of typical formulation where I have X and C plus, X and C minus. Again, X, which is the point or the position vector I'm classifying at this point. I'm just classifying using my knowledge from this space. Okay, so X and C plus, X and C minus, and this is called the B term. All this plus half of C minus, C plus, okay? As shown here, this B. So this B is called like this. That's just a way of a terminology, so to speak, okay? If we're applying some kernel function to modify our space, the kernel function will actually happen at this point. Remember, here I am computing my C++. If I substitute this by the result of C++, what is C++ for me? It's the same as the average, considering only the positive elements. Take a look here, only the positive elements. Varying I, which corresponds, which is an index to vary the elements or the examples I have in my training set. Okay, and X is basically the position vector, the new position vector I'm classifying. Okay. And here, the negative is the same as computing the average for every negative element, computing the inner product over here. Why this is possible? Again, the inner product is an inner transformation. So given this guy over here is defined by X, comma, the sum or the average, given the sum of every positive element I have in my space, and this, the average given every negative element I have in my space, given I have the sum over here inside and the sum inside, I can just put the sum outside like this. And here the same, the sum would be inside and I can just put it outside like in here. And what is nice, n plus b, of course, and b is defined over here. So what I call a kernel function is exactly the application of a transformation on X and on Xi before computing the dot product. Before computing this dot product, I can transform X to go to a different space. I can transform Xi also in a different vector, lead all those two vectors, all those two vectors in a different space, and in that particular space, I compute the dot product as shown here. I usually use this terminology to show that we've got a space transformation, or aka kernelization of our space. I'm going to show that for you guys, don't worry. The same happens in here. Take a look. You know what's interesting over here? Of course, B had here C minus to the square and C plus to the square. Of course, here I had like an inner product, as shown here, an inner product of C minus, and here of C plus, C plus. That's the same as having sum of something to compute the average, and here too. I've got two sums over here. I can just put those two sums outside. That's happening over here, but I'm just showing, using a single sum, that both terms I and J are varying to allow this computation. We're going to implement that. Actually, you're going to implement right now. So let's go to let's open our code. Those are the central points. Of course, here we have C plus and C minus. I'm just going to proceed with this. How can I compute the classification? As shown here, basically, I have to perform the inner product of some X by C plus, like this. This is the inner product, okay, guys? Minus X, inner product, by C minus, as shown here, plus B. What is B? B is basically half, okay, times the inner product of C minus, inner product by C minus C plus, inner product by C plus. Let's see the results. This is nice, okay? And my final result will be given as y in terms of the sine function of this. What is x? Oof, no. Could I, for example, compute for multiple x's? Yeah, but let's start with some value for x. You guys know that the average, like 10, 10, is the positive side. So let's see if this returns like, if I print it, if it returns like positive 1. It should be. Let's run it like this. So source like this, first algorithm, and it returns positive 1. The plot is still the same. We are going to adopt this plot. I think it's nice to see what's happening if we change the position vectors being classified over here. Well, let's consider a different x, like minus 10 should be minus 1, the result, right? If I run this, it should be minus 1. Yeah, right, that's perfect. Oh, that's really nice. What happens if I had a position vector like minus 5 over here? It should be negative 1 as well. So minus 5, or maybe minus 4, minus 6 should be negative 1. Let's see the result. Take a look. Ooh, right, perfect, negative 1. What happens if it were positive 4 and positive 6? It should be positive 1, and it is, okay? What I'm going to do right now is something that I consider interesting. You know why? We could have some like 2 4s over here. Okay? I'm going to start with 2 4s. This one is going to vary the first attribute, attribute 1. Attribute 1 will vary in range from minus 10 to plus 10, and I will build up, let's use like 100 points. I'm going to do the same about attribute 2. And you know what's interesting? I'm going to compose attribute 1 and attribute 2 to form x. Attribute 2. Both together will represent x for me. And what's nice about this? I'm going to build up a matrix over here. Okay. This matrix with let's call like x new and y new. Y new will be the classes, the class labels we found. Okay. So what's going to happen here is this. After applying my classifier, I will just save up in x new along the rows. I will just concatenate my x, just to say, okay, this is my x. And in terms of y new, I will just add up the classification result like this. Okay, so I run it like this. It's going to take some time, not too much. Yeah, finished. You know what's nice? I can plot x new now. What is interesting is this. I can plot x new like this using colors given by y new. I'm going to sum up not 2 but 3. Just to make it different, maybe, or maybe like, yeah, it could be 3. Let's see what's going to happen. Take a look, guys. That's so interesting. So I'm just considering every possibility from, not every, of course, but many possibilities from minus 10 to plus 10, and from minus 10 plus 10 in this dimension, and giving those points to our classifier. All those in red are negatives, and those in blue are positives. So nice. I could even consider, instead of minus 10 to plus 10, could be like minus 15 to plus 15. It would provide like a better grid of points, in my opinion. When I run it, let's put this plot inside our code, because it's going to run and provide the classification result. It's so nice to have it. Take a look. So nice. That's where our hyperplane lies on. It lies exactly on this line over here, guys, as you might see. It is exactly at the point in which we have the change in between the negative to the positive class over here. If you guys prefer, I can even use the same colors. Yeah, I think that's probably even better. Okay, same colors. Yeah, that's much better. Much better. Okay, so here we are just seeing the effects of considering this first algorithm. But you know what? Oh, I could have like a more complex space requiring some kernel function, some kernelization over here, What is a kernel function? How it changes my space? Okay, let's go to the next example. You know what's nice? I'm going to create like a second algorithm over here. I'm going to define a different space. I think I will do something like this. Considering the R norm or the Gaussian function, bidimensional Gaussian function, again, with a mean equals to 0 and standard deviation could be like 20.25, I could come up with 100 points in the same way, and the second dimension, it will be the same. Okay. This is going to provide my input space X. You know what's interesting? I will load a different package, a different library in R over here. This is a library for dynamical systems. But in my case, I'm going to use it to make a quite interesting transformation in this sinusoidal function. I will define a sinusoidal function from 0 to 9, given that I will come up with like 1025 observations. This is not out of the blue. This is something I tested before. This is, if I plot this is a sine function. However, there is a quite interesting function inside this package, which is the function embed. This function implements Chaikin's embedding theorem. This is an embedding theorem that reconstructs my data. In my case, I'm just performing that on my sinusoidal function plus some noise, and you guys will see the noise over here like this, just to come up with a very nice example. Doesn't matter actually, this command is not even necessary in the context we are working on here, but it's going to be so way interesting. You're gonna see. So I'm going to bind this in X, okay? And now what I'm going to have in Y will be this. The first 1000 observations will be, could be negative. Yeah, could be negative. They're going to be negative the first 100, sorry. Oh, I defined 1025, so here we better use 1000. So the first 1000 observations will be negative, and the following 1000 will belong to the positive class. You know what's going to happen here? I'm going to plot this. It doesn't matter the magic I did over here. What it matters is just the way my data set looks like. I'm going to load my second algorithm. You're going to see something that I suppose will be quite interesting. Of course, there is a mistake over here. I think I forgot. Yeah, I forgot like a parenthesis over there. That's enough. That's all? No, it's not. What's happening here? Okay, I think I know. Let's see. Oh, yeah. There's a parenthesis missing over here. Sorry, guys. Over there. Yeah. I think that's all. Let's see. Exactly what I wanted. But actually, I will reduce the noise because the noise here is really, really large. And I will plot, of course, using PCH20 and CEX equals to 2. Yeah, could be 2. Maybe I will reduce my noise like to 0.2 instead of 25, and here also like 0.2 instead of 25, just to make it more, let's say, less stochastic, even less. I think it would be like 0.15 over here. I think that's enough for our second example before going to more complex examples. Oh, that's really, really nice. Really nice. Okay. What is nice now is this. You know what I'm going to do? I'm going to try to classify this space, but what is the problem? If I come up with the average of the central points, which are negative, I think those are negative examples. The average will be here at the middle. And the average for the positives will also be at the middle. How can I classify those if the both averages are around the same? That's a problem. I don't know how to solve that. How can I compute that? Of course, I could take x from the first to the example at the position 1000 and compute co-means. Take a look at the average. And take a look at the average if we go from the 1001 to 2000. It's around the same. How could I compute the differences? Wow, I don't know. I should come up with some space transformation. The question that stays here is it possible to transform this space and come up with a more meaningful space? Yeah. So what I'm going to do here is the kernel transformation. My proposition for you guys will be this. My kernel transformation will be a k function. Actually, will be even more interesting. Will be a phi function. That's a typical name people use in books, so that's why it will be a function. I will receive a vector, which is in my space, a vector x, which is basically a row from this space. And what I'm going to do with this vector, I'll just return it like this. Return a new vector. This new vector will be x, the first element of x, to the square, the square root of 2 multiplied by the first element multiplied by the second element of the same vector, and the second element to the square. This will be my space transformation. What I'm going to do now is apply that space transformation. I'm just going to call it space transformation instead of kernel. But that's a kernel. Okay, doesn't matter. I'm going to do something like this. For every example you've got, from 1 to the number of examples you've got in matrix X, please apply this kernel transformation. Apply it on the example at the position I. And you are going to save that in an uppercase matrix phi like this. That will be my matrix containing the new results like this. It's going to contain all results. You know what's interesting? Next, I will plot for you using a package called RGL. RGL has got a function called plot3D, which receives my three-dimensional space and the colors as before. The colors are the same. It's going to plot for me. We're going to see the effect of this kernel transformation. Let's see what's going to happen over here. So let's load. Okay, before looking at that space, there's a problem with the colors again. Sorry guys, I forgot to sum up 2 over here. But I don't want you guys to see this at this moment. So I'm just going to leave it like this and cover it up. Okay. So let's load my code once more. No. Yeah. So this is my original bidimensional space. What happens when I perform this transformation? I'm leaving the second dimensional space to a third dimensional space. This third dimensional space is assessing the first dimension to the square, what is the same as some sort of correlation from the first to the first dimension, and a correlation in between the first and the second dimension, and a correlation in terms of the second dimension. When I plot this using a plot 3D, take a look now. What you guys have, take a look. It is so way interesting. I think I could use like plot, maybe like RGL, plot 3D phi colors equals to y plus 2 and PCH equals 20, and what is the other option? It is CEX equals 2. No, it doesn't work. CX equals 5. No, it doesn't work. Yeah, this guy has like no meaning. Probably there is like a different parameterization here. Just don't know it. Doesn't matter. Okay, I'm going to open up. Let's take a look at this space. I'm going to rotate it. Take a look. Wow, it's taking time to rotate. Wow. So slow. Sorry guys, it's slow. Because of my machine, because of my computer. I'm trying to rotate, but it's taking forever to rotate. Let's try to rotate once more. Wow. Let's go. Rotate, please. Okay, let's consider like small space. Let's see if the rotation gets better. Okay. Take a look now. I've got 3 dimensions. What is the meaning of the first dimension, which is in, let me see, first dimension, it is in here. This first dimension means the first dimension of the 2-dimensional space to the square. This one means the square root of 2 times the first and the second dimension per vector, and this means the third dimension. What you guys see doesn't matter, but actually the dimensions are here. That's the most important. You know what's interesting? You guys might notice that now I can cut over here with a hyperplane. But my hyperplane will not be a linear function, a typical single-dimensional linear function. It will be a plane, a second dimension function, actually cutting here. It will just cut like this. So what is interesting here is, in my original space, I cannot work with a hyperplane cutting what is positive from what is negative. But in my high-dimensional space, I can. It's going to cut like this and here. Okay, like disconnecting blacks from the green points over there. You know what's interesting here? How could I do that? After having this transformation, the algorithm is basically the same. So I could just open here, take a look. I'm just going to open here, like split my first algorithm. What's going to happen with all this? All this is going to be the same. So I could just copy it and I could just paste it like this over here. and just close my first algorithm and stay with my second. So now what I am going to do is this. I will compute the call-means not for the regional space, but for this space phi. Not for the regional space, but for the space phi. Those are the results for C- and C+ on top of phi instead of on top of the regional space. What I'm going to do now is I'm not going to plot this central point. I think it's not necessary. You know what's interesting? Now we will have, of course, central points over here. Okay. I will have this. Oh, yeah, I don't need this because I will not plot. I will have just the new points and the results of the new points. Of course, now I don't have 2 dimensions, I have 3 dimensions. And dimensions are like roughly from minus 1.5 to minus 1.5. So I'm going to vary the first attribute from minus 1.5 to 1.5, minus 1.5 to 1.5. The third attribute will be also from minus 1.5 to 1.5, but instead of like 100 points, let's try like 25 points only. Because of course now the complexity will be greater. As you guys know, it will be n to the third. Okay. So our x to be applied now in our algorithm will not be only composed of attribute 2 and attribute 1 and attribute 2, it will also be formed by attribute 3. That's why we have this. Here I will compute this, I will compute that, the rest is just the same, okay? And of course, I need somehow to plot my results over here. How can I plot those? I can just use the same like this. So I can plot, instead of plotting phi, I think it's possible to plot like points 3D. Let's see if there is a function in RGL which is like points. Ah, so nice, points 3D. Yeah, I didn't know it. So I'm going to plot like x new and y new plus 2, just to make the correction in the colors, right? Yeah, let's do it. That's all. Yeah. Let's see what's going to happen with my second algorithm. It's going to take like some time. Wow, so way interesting. It's a little hard to see, but the hyperplane. No, it's maybe like this is easier. The hyperplane is cutting here. You guys can see that the positives are on one side, the negatives are on the other side. So interesting. You see, I'm cutting here. So if my original space, like this, is not enough to come up with a solution, I can apply a space transformation. In my case, the space transformation leaves the second dimensional space and goes to the third dimensional space. Oh, I want to understand better about those space transformations. Don't worry. We're going to have probably a couple or maybe 3 classes maybe on that. I think it's more like a couple of classes on that subject. So don't worry. What you need to worry about at this point is how this very basic algorithm works. Okay? Now I just leave you guys with this as homework. Try to re-implement this using your code and not mine. Okay? That's all for, I suppose, yeah, that's all for this class, and we get back in the next video. See you guys.